Last lesson of the unit, angle properties of polygons. So we're moving a little bit away from triangles, just a little bit, but all the stuff we've learned is gonna help us out. So first of all, what is a polygon? A polygon is a closed shape made up of straight line segments. And by a closed shape, I mean like a square, like a triangle. The ends of each line segment connect. So a circle is a closed shape, but a circle isn't a polygon because a circle is curvy. So here's the two kinds of polygons we can have. A convex and a concave. And again, these are supposed to be straight lines. So concave meaning goes in, like a cave goes in. So here's a simple little exercise. Figure out the interior angles of a polygon. Remember, we did the interior triangles of a triangle, and we found the interior angles of a triangle always add up to 180 degrees. So right now, just pause the video and have a look at this and see how might you determine the sum of the measures of the interior angles of this pentagon, a five-sided figure below. So I would imagine that you did two things. The first thing you did is you broke this into a triangle and a rectangle. And we know the interior angles of a triangle all add up to 180. And we know a rectangle has 490 degrees, and that would be 360 degrees. And then we could figure out the answer. So you may have done that. Or another thing you may have done is you may have made three triangles. And in making three triangles, each one of those triangles has an interior angle of 180 degrees, and we have three of them, so there's the exact same answer. 3 times 180, and they both equal 540. So that's what you probably did. There's no formula. There's no idea in your head about interior angles of a polygon, meaning anything bigger than a rectangle. So have a look at this one right here. And again, in a minute, pause the video and you try it and see if you do the same thing I might do. So we want to figure out the measure of the interior angles of this pentagon. It has 5 sides to it. And again, you could measure it, I guess, but see if you can do it without measuring. Okay, so one of the things that you might have done is you might have went ahead with the idea that you did above, and you might have made triangles. And as long as we know how to make those triangles, then it's a pretty straightforward exercise. And this is what the ancient mathematicians did. They relied on triangles. So as long as you start at one corner and go systematically, go from there, then you should be able to draw a number of triangles. But the main idea here is you do not cross lines. So based on what you may have done, what I just talked about, it's as simple as that right there. So if I drew a triangle, I can make a line there, and I made 2 triangles, and I can't do anything else. Now here's what I mean about lines do not cross. If you went ahead and drew another line like that, then all of a sudden you see 4 triangles, and we're going to come up with the wrong answer. So you could draw the red line by itself, you could draw the green line by itself, you still get 2 triangles, but you have to draw it systematically, and by that I mean lines don't cross. Okay, so this is going to be a lot of little, pause the video and fill it in yourself, and I hope you do that. because it's really straightforward. So if you imagined, and you could do your work on a rough piece of paper, if we had a triangle that has three sides, then you only can make one triangle. With the triangle, the sum of the interior angles is 180. Well, if you had a quadrilateral, quad means four-sided figure, like a rectangle, well, you can make two triangles. And again, we know right now that that would mean we have 360 degrees altogether. Well, a pentagon, we've already done it on the previous page. We could make three triangles, and each one of those triangles has 180 degrees, and away we go. So, etc., etc. So I'm just going to fill this out, and hopefully you've done it already. And again, just by counting how many triangles there are, or adding up all the 180 degrees at a time, then we can see, without a formula for every shape, we can just use triangles. So triangles are really good for helping other shapes. So again, what I'd like you to do, before you maybe copy what I say, for these two things, make a conjecture about the relationship between the number of sides, between the sum of the interior angles and the number of sides. So look at columns 3 and 4 above, and can you make a conjecture? Can you come up with a little formula or relationship? And similarly for columns 2 and 4. Okay, so if you tried that, you might have noticed something like this. 180 times the number of triangles equals the sum of the interior angles. And if you didn't notice that, go have a look now. 180 times 1 is 180, 180 times 2 is 360, etc., all the way down to 180 times 6 is 180. So what we're doing in this thing here, we're relating columns. So we're relating columns 3 and 4. There's a nice simple little relationship. Well, can you make what was your conjecture between the sum of the interior angles and the number of sides of a pentagon? So again, you're looking at columns 2 and 4. And maybe what you noticed is this: 180 times the number of sides. Now again, a quadrilateral has 4 sides. A pentagon has 5 sides minus 2 equals the sum of the interior angles. Maybe you noticed that. Let's do an example with the hexagon. So a hexagon has 6 sides. So we're going to have 180 times, hexagon has 6 sides minus 2. That's going to be 180 times 4, which is 720, which is what we found when we simply divided it up. So the really nice thing about this thing is you can answer a question 2 different ways. You can simply draw on the picture and count how many triangles and do a little multiplication, or you can use a little formula if you want. And if I wrote down the formula, here's what it would be. The sum of the interior angles, the sum of interior angles is equal to 180 n minus 2, and n represents the number of sides of the polygon. So look at this example right here. We could pick a starting spot, like right here, and start making a bunch of triangles, etc., all the way around like that, and then count how many triangles we had, and then multiply that number by 180. But we have that really nice little formula, and it says the sum is equal to 180 times the number of sides, which is 15, minus 2. So we get 180 times 13, which is equal to 2,340 degrees. So in that pentadecadon, that 15-sided figure, I don't know what the angles are right now, but I know all of them at the 2340. Now, in this particular question, what we're then asked to do is figure out the measure of each interior angle. And the thing that's really important is the word regular. So a regular polygon means all sides and angles are equal. So for instance, a square. A square is a regular quadrilateral. All the sides are equal, all the angles equal 90. An equilateral triangle is a regular triangle. 3 angles of 60 degrees and all 3 sides are equal. So if we know the sum of all the angles to figure out one interior angle, like one angle, that's equal to the total divided by how many? And there are 15 of them. And when you do that, you get each one is 156 degrees. So again, triangles are helping us with the other shapes too. So just like with triangles, we looked at the exterior angle, and we found the exterior angle of triangles is always 360. So again, right here, if we wanted to know the sum of these exterior angles, I would hope you would look and recognize that all those angles are 90 degrees because they're angles on a line. So what we should see here is the exterior angles of this rectangle add up to 360 degrees as well. And that's kind of really interesting. So here's where we are now. We know the sum of the exterior angles of a triangle are 360, and the sum of exterior angles of a quadrilateral is 360. So what do you think the sum of exterior angles of any polygon are? So your conjecture might be 360 because the first two. So let's see if we can prove it. Here's our statement. Here's our justification. So let's go ahead and do this. Now again, remember what we want to show. We want to show that w, x, y, z is equal to 360. W, x, y, z is equal to 360. So eventually that's what I want to show. So here's what we know. Again, we just know this. Angle A plus angle W equal 180. And all the way around, angle B plus angle X equal 180. Angle C plus angle Y equals 180. And finally, angle D plus angle Z equals 180. And that is all angles, or angles on a line are supplementary, so I'll put supplementary. Now remember, we want to show that these things right here equal 360. That's going to be our last statement. So, but we do know something else. We do know that ABCD equals 360, interior angles of a quad. So we know this plus this equal 360. And again, interior angles of a quadrilateral. Right? Now, if we add all of the inside together and all of the outside together, we get angle A plus angle B plus angle C plus angle D plus angle all the way up to angle Y plus angle Z. And we know they equal 720 degrees because we're putting together all of that stuff above. Now here's what I'm simply going to do. Instead of the first part, ABCD, which is right here, we know that ABCD equals 360. So here's what we know. We know 360 degrees plus angle W plus angle X plus angle Y plus angle Z equals 720, right? And basically all I did was I substituted. I put 360 instead of that. So finally we get what we want. When we move the 360 to the other side, we get what we want. And again, I'm just going to call it algebra. We subtracted 360 from both sides. So there we go. Every polygon, every convex polygon has exterior angles of 360. So would this proof hold for any convex. So, you know, we did this non-regular, non-nice rectangular thing, and it would. So the proof that we did, we could make it bigger. We could do 5 sides. We could do 6 sides. It would still work exactly the same way. It would be a lot messier. It would take us longer, but we could. So if we were to add another corner, so again, you know, when you go from a 4-sided to a 5-sided, you're just adding another corner. We would be adding another 180 degrees. So be adding, again, instead of a plus x, that's 180. We'd add 5 of them instead of 6 of them. One more set of supplementary angles. So we'd be adding that to our thing. Again, another 180 degrees, just like the 4 in this one. But we would also, counterbalancing this, with the addition of one more interior triangle, if we're going to draw it. And that would be that other 180 degrees. So again, when we add something, we take it away, and that would keep on going regardless of the number of sides.